Hello everybody. Today we're going to be learning about cells, electrochemical cells. These are going to be the setups, the compartments that we have that will allow an electrochemical reaction to occur and start generating some electricity for us. Now when you look at this first diagram, you can see that looks a little overwhelming, doesn't it? There's a lot of pieces to these cells. The nice thing is that they're always going to have the same components. We're always going to need to be labeling the same things. So I'm going to walk you through how we're going to go do that. Thing with cells is that they're very, very helpful to us, right? Like even things like batteries. It's a great way to be able to generate some electricity from our chemicals. So you can pop in a battery and make your device work, right? So there's different types of cells. The first type we're going to look at is called galvanic cell. Sometimes you may hear it called a voltaic cell. It means exactly the same thing. I personally do not care which term you use. Just make sure you know both of them so you don't get confused if you're doing extra practice. You don't get confused when you see one or the other on the AP test. The special thing about galvanic cells is that they are thermodynamically favorable. And if you remember what that means, it means that that reaction is going to take place spontaneously. It's going to happen all by itself. I do not have to apply any kind of outside force to make it happen. So you set the cell up, and as long as you set it up correctly and hook up all the parts correctly, the reaction will begin to occur, and you'll start generating that electricity. When it comes to drawing our cells, there's going to be a lot of things to include. The first thing we need to do is kind of sketch out the basics. So you can see here I have two beakers. The beakers are each filled with solution. Draw a little squiggly line on your drawing so you can tell that there's supposed to be liquid in there. We have these strips of metal. Those are called electrodes. We will have a wire connecting the electrodes to each other, and we will have something called a salt bridge, which will be submerged into the liquid. It has to actually be inside the liquid, and that salt bridge is going to be a source of ions, and we'll explain why we need that later. And if you look, you kind of make a circle here, don't you? You can kind of go through this in one big loop. Right? That's called a circuit. Okay, maybe you heard that term maybe in a physics class before. Okay. So the first step is drawing these basics out. You will typically be told what your electrodes are made of. So electrodes will be pieces of metal. You can see at the top here, manganese and nickel this time. And now it's going to be time to start labeling your cell. The first step to labeling your cell is figuring out what your electrodes are going to be doing. One of your electrodes needs to be oxidized and one needs to be reduced. Okay, so we have to have one losing electrons and one gaining the electrons. If you remember from our previous lessons, you're going to need to look at your reduction tables to figure out which metal is going to do which. So I find manganese, I find nickel, and then I'm looking for the one that is a more positive reduction value. Negative 0.25 is more positive than negative 1.18. So nickel will be the one that's reduced. Nickel is going to be gaining electrons when my circuit is working, when my cell is working. Manganese is going to be the metal getting rid of the electrons. It's going to be supplying those electrons. We have two sides to a cell. We have an anode and a cathode. And the electrodes get stuck into each side, right? We have to figure out which side is the anode and which side is the cathode. Anode means electrons are being lost. From the previous slide, we saw that the manganese is going to be the one losing the electrons, Remember our little mnemonic here, right? Leo goes Ger. Cathode is going to be the side where the electrons are being gained. That'll be the nickel side. So now we can label anode goes with manganese, cathode goes with nickel. Label your electrodes. Sometimes that's easier to do kind of next to the electrode. Label what's anode, label what's cathode. I like to do that underneath. Okay. Now the next thing we're going to have to label is what solutions are inside these beakers. What do I have over here and what do I have over here? The solutions should have a common ion with the electrode. So whatever solution is down here will have manganese ions in it. And whatever over here will have nickel ions in it. They will usually tell you what the cation is that would accompany it. Like, do you have manganese nitrate, right? Maybe that's what you have. They'll tell you what the compound is that made these solutions. It should be soluble though, right? Because we want manganese ions floating around and we want nickel ions floating around. Now we have electrodes labeled, we have anode and cathode, we have our solutions, and now we got to label which direction the electrons are going to flow. Where is the current going to go? What direction are they moving? We saw earlier, right, the anode side is where electrons are being lost. Then they have to go somewhere, right? Well, they're going to go from the anode to the cathode. I always remember that as it's alphabetical, right? You're going to go from anode to cathode. So up here near my wire, I am literally going to draw an arrow and I'm going to label it with electrons like that. That tells people that the electrons are going to come through this wire. They're going to go through here and into the other side. Now, as this is running, this strip of neutral metal is losing electrons, turning into aqueous ions, and it kind of comes off and starts floating around in the beaker. That means the size of your anode starts to get smaller. It's literally going to start to disappear. Not disappear, it's not magic, but you know what I mean. We're going to be losing mass because the solid is turning into aqueous ions. The cathode will be opposite. This cathode is going to have nickel ions turning back into solid and they're going to stick onto the electrode. And your cathode starts to get bigger. So I have a really silly picture to help you remember this. I think it's absolutely ridiculously silly, but it's very memorable. And I have a little mnemonic that goes with it. So we are going to say that a red cat gains what an ox loses. So this poor skinny little red cat over here, reduction cathode, is going to be gaining mass, and that mass is because this poor ox over here, he's going to be losing mass. An-ox, anode, oxidation. Losing mass over here, gaining mass over here. Okay. So we're gaining not just electrons, but we'll be gaining mass. All right, the next thing that we want to do is label some pluses and minuses onto our drawing. So once again, we know anode is where the electrons are being lost. And what that means is this is a source of electrons. Sometimes they may say it's electron rich. It has electrons to be getting rid of, right? So we are going to label that with a negative sign. Whereas the cathode is where the electrons are being gained. It's drawing the electrons towards it. There's not enough electrons here, so it's needing to get them. We say that they are electron deficient, and we will use a positive sign over here. So we've labeled our arrow with our electrons, but then we should also come in here and label with some little circles negative and positive. And like I showed you with that funny little mnemonic, right? When we're losing those electrons and gaining electrons, it's the same for the mass. Here we're going to have solid manganese turning into aqueous manganese. This will literally start to weigh less. The cathode is going to start getting more metal deposited onto it. Sometimes you'll hear the word plated. The solid metal, neutral metal, will get stuck to this electrode, and it will be gaining that mass. Okay. I'm hoping what you're seeing is that kind of identifying one aspect of your cell can kind of start giving you this domino effect of more pieces of information that you can determine if you stop to think about which thing needs to be reduced versus oxidized. It kind of tells you everything you need to know. Don't forget our little circles, right? So not just electrons, but also the mass. All right, this is the classic picture that you'll see in a textbook. And they've drawn their little circuit, they've labeled anode and cathode, they've told you what the metals are, they've told you what the solutions are, they have their little salt bridge, okay, they're showing you where the electrons are going, or minus and positive, kind of everything is labeled like we've been talking about. But what I love about these drawings is they zoom in on the electrode. So here we have an atomic view of what's happening on, for example, this time it's zinc, right? We have zinc ions that are getting made. We have neutral zinc, solid, getting rid of electrons, and then it detaches. It's not solid anymore when it's an ion. It becomes aqueous and starts floating around in the solution. Versus the cathode is backwards. We have electrons coming in the cathode, and now there's all these electrons, and so these copper ions grab onto those electrons, they take those electrons, they gain them, and now it's neutral. And if you have neutral metal, it's not going to be aqueous anymore, is it? It's now going to be a solid, and it'll get deposited and stuck onto the electrode. So you can see here, right, it didn't have to be manganese and nickel. It can be different metals, right? As long as one is oxidized and one is reduced, that will work. One of the key things that I really suggest is taking the time to write out your little half reactions. I see way too many people trying to do these cell labelings, trying to do electrochem problems, and they never write out their equations. It's so important. Just like in stoichiometry, you should not be doing stoichiometry without a balanced equation. I don't want you drawing cells without some half reactions happening. Okay, when you can refer back to them, it can help you answer lots of types of questions. All right, now let's get to the salt bridge part. What's the point of a salt bridge? Okay, the salt bridge is going to help with the charges that are happening, okay? We want to maintain what we call the charge balance. So we have our anode, metal becoming aqueous ions. In that process, you start making more manganese ions, don't you? You're making a bunch of cations. Well, cations don't want to float around by themselves without anions there to balance them out. So we need something to supply some anions. When I make more manganese, I got to get some anions added as well to balance it out. On the cathode side, we're making neutral metal. In that process, we are using up some of the nickel ions. We have a bunch of, maybe let's pretend it was nitrate still floating around in this beaker, but now we don't have enough cations to balance things anymore. So we need something to add cations while the cell is running. Okay. Remember, this side negative, this side positive. One of the things that's nice if you take the time to label your negative and positive is that can be a very good reminder of which ion needs to go into the solution from the salt bridge. Your anion needs to go into the anode. The negative ion goes towards the negative electrode, doesn't it, to be a source of those anions. Whereas your cation is going to go into the cathode, the positive side, to replenish all those cations that are being used up. The key is you want to use a salt that is going to be soluble, and you want to use a salt that's not going to cause some kind of weird, crazy side reaction. Now, they don't really expect you to know a ton of different examples of what might be a good salt bridge, but potassium chloride is one of the absolute classics. That would be the kind of thing you may want to just memorize so that if you're kind of stuck in that moment, you have an example to pull from. Okay. Very often, they're going to ask you a question that says something like, what's wrong with this setup? What's wrong with this cell the student created? And they'll show you a diagram with no salt bridge. And the thing is, if you don't have a salt bridge, as the cell runs, you start getting way too many cations on one side and not enough on the other. You end up with what's called an imbalance of charge. And after a little while, it will get bad enough that your cell won't work anymore. We say the cell dies. You just can't keep going. And so what the salt bridge does is it says, it gives the ions that are needed to keep the charge balance, to keep your cell working, and we say it, quote, completes the circuit and maintains charge balance. This is a phrase I want you to memorize, okay? I want that in your brain somewhere because they very often will ask you about that. The only way those electrons can keep flowing from our anode to our cathode is if that salt bridge keeps those charges balanced. Okay. Every once in a while, it won't be an actual salt bridge. It'll be something else. Oh, real quick, I didn't even describe what this actually physically is. Salt bridges are going to be, a salt packed into here. And usually you put little blobs of maybe a cotton ball or gauze or something in here so that it all just doesn't dump out at one time. And very often you'll have a glass tube, or maybe you'll have a flexible kind of a tube. And then it'll be packed with an actual salt, physical salt. The water will wick up a little bit, right? So you'll have some here that will start to be able to dissociate and become aqueous and enter into the beaker. There are other ways to accomplish the same thing called a membrane. So once in a while you'll notice instead of two totally separate beakers with a salt bridge, They draw one container with some kind of line down the middle. That line represents the porous membrane, and it's a special type of material that allows certain ions to pass through it. Okay, way more complicated than anything I have in my classroom. We have salt bridges. That's what we have. Okay, so here, some ions will be able to go through it. And you'll notice the cations from one side can travel to the other side where they are needed. The anions from one side can travel to the other side where they are needed. So the charge can still be balanced. Your cations and anions can still go where they're necessary, but you don't have to have a separate piece of equipment. You just have this membrane in between. And then you'll be able to have your electrons flowing. So at the end of the day, the key is identifying where you're having oxidation and reduction. So anode, oxidation, an, ox, loses, right? You have anions going to this compartment, to the negative side, and the anox loses weight along with those electrons. The cathode is all the opposite. That's the nice thing about electrochem. If you can know one side, you instantly know the opposite side. It's all backwards. The cathode can be a very helpful place to us from a practical standpoint. We can coat things with metals that we're interested in. That's called electroplating. Maybe I want silver to get stuck onto my spoon or something. That's always the classic example. Well, the ions turning back into a neutral solid takes place at that cathode, so that's where it would happen. All right, other kind of cell, here we go. Electrolytic cells. These are the opposite. They are not thermodynamically favorable. They are not going to happen all by themselves. You need to hook them up to some kind of outside electrical source in order for them to happen. You're going to have to supply electricity to force the reaction to run in the opposite direction that it wants to be running. So let's look at an example for this. Let's say we're going to have zinc and copper electrodes. I'm going to look at my reduction table. I find the reaction for zinc and for copper. I look here and I say, hey, this one's more positive. It's more likely to be reduced, and this one will therefore be oxidized. If I hooked that all up, that would be a galvanic cell. It would run all by itself, and it would do exactly what I would expect it to do. But what if I don't want to go this direction? What if I want, instead of making neutral copper, I have some reason I want neutral zinc instead? I don't want zinc to be oxidized. I want to force the zinc to be reduced. That's where we have to make an adaptation to our cell. I got to hook my cell up to some outside source. So what we do, right here you can see inside this wire, I'm going to stick on something like a battery, for example. Okay, I'm going to force this to go the non-thermodynamically favorable way. Remember, something being non-thermodynamically favorable doesn't mean it can't happen. It means you gotta force it to happen. And that's exactly what I'm going to do. The way we talk about this is we say we're going to drive the electrons the other direction. It's kind of like swimming upstream, isn't it? Naturally, we would float down the river downstream, and instead we're going to be trying to swim the opposite direction upstream. We're going to drive going up. Okay, so the key here is if you have to draw an electrolytic cell, you got to add something like this indicating that you have an outside source of electrons here. You are still going to label the anode as a loss of electrons. you are still labeling gaining as cathode. That doesn't change. You still show the electrons going towards the cathode. You still got to use a salt bridge. The ions will still go in the same direction. The difference is we are going to use plus for anode and minus for cathode. So we identify the opposite oxidation reduction than we would expect, and then we switch the pluses and minuses. The reason is the electrons have to come off of this anode. They go in here and they're leaving that side and going towards the cathode side. I think one of the things that confuses people is that there is no standard, accepted, required way of which side you make anode versus cathode. And so you may be super used to putting anode on the left and cathode on the right, but then like for example here, we've swapped these, haven't we? So that's why it's really important that you just go through very systematically. You get your half reactions, you figure out which direction things are going, you label all your parts, right? Don't worry too much about what's on the left versus the right, just make sure things are going in the right direction. So here, if the electrons are coming off of this battery towards the cathode, this is now very electron rich, isn't it? And that's why we make it a negative. This side is losing those electrons and it's not going to be having a bunch. It's electron poor, deficient. That's why we label it as a positive. So that key to electrolytic cells is it's going the opposite of what we would expect because we're forcing it to happen. So reverse what you are making oxidized and reduced. Add this extra voltage source. Go through the process of labeling everything like normal. And ox is still losing electrons. Okay, a red cat is still gaining electrons. And then the very last thing is swap the plus and minus like you normally do because it's electrolytic and we're using those terms of electron rich and electron deficient a little differently, aren't we? Okay. For a galvanic cell, we're taking chemical energy, returning it into electrical energy. We get a nice positive cell potential, which means we have a negative G. It's spontaneous, thermodynamically favorable. We're going to have minuses and pluses assigned like you see here. We're thinking thoughtfully about what direction those electrons are moving through the wire, going from one compartment to the other in our cell. An electrolytic cell, we're now going to use that outside electrical source to make our chemical reaction happen, right? We're going backwards here. This is not going to be a favorable reaction. This is negative cell potential, positive delta G. You're going to swap those pluses and minuses because those electrons heading towards that cathode are coming from your outside source. They come in from the battery, they enter the cathode, and they're leaving that anode. All right, let's do a problem where we have to figure out if something would be galvanic or electrolytic. Okay, we're going to have zinc and copper. If I look here, my copper is more positive. My zinc is more negative. I'm going to flip my equation. I'm going to flip the sign on E. I'm going to add them together. And now if I have neutral zinc turning into ions, and I have ions of copper turning into neutral copper, I see that I would have a positive cell potential. That means it's spontaneous. So if I were to run my cell like this, right, with zinc as my anode and copper as my cathode, this would be spontaneous. The other problem I see is on a question like this, people will just tell me, I don't know where to start. Start by looking at what they drew for you. Or maybe they give you a chemical equation they want to use. Look at it, okay? We got to actually inspect and observe what they're providing us. They provided us this diagram. Neutral zinc losing electrons, right? Now let's look at one that's going to be a little different. Here, do you see how they told me a cell is undergoing this reaction? Okay, we see sodium chloride breaking apart, forming neutral sodium and chlorine gas. I am going to look at my reduction tables. I find sodium, chlorine gas, I get my values, and you're first going to think to yourself, oh look, okay, this one's most positive. That's the one that's going to be reduced. No, it's not. Look at your chemical reaction carefully. I do not have chlorine gas as a reactant, do I? It flat out told me my chlorine is going to be a product. This needs to get flipped. I have sodium ions and chloride ions. The equation is flat out telling me that even though this would not be my preferred reaction to use because it's more negative here, that it is what's happening. This one is going to be reduced, even though my numbers would imply otherwise. And I have to flip this one. Even though it wants to be reduced, in this chemical equation, I have chloride ions that are getting turned into chlorine gas. It's being oxidized, losing electrons. I have to flip it, don't I? Do not argue with the reaction that they give you. If they tell you this is what's happening and it goes against what you would predict, that means it's electrolytic, isn't it? So what I'm going to do is I'm going to flip this equation so that I get things going the right direction to match my cell reaction. And I'm going to flip the sign on my cell potential as well. So I have my sodium ion becoming neutral sodium, just like it shows here. And I'm going to have my chloride ions releasing electrons, being oxidized. Now it's negative 1.36. Remember, just because this would need to be multiplied by 2 does not mean I need to multiply my cell potential by 2. Remember, we just add cell potentials without worrying about it. A little bit different than a normal Hess law problem, right? I add it up, I get a negative voltage. Now it's electrolytic, it's non-spontaneous, delta G is positive. And so we have to understand that that means this will not happen by itself. We are not going to get salt to spontaneously break apart like this, are we? But if I were to hook it up to an outside electrical source, I could do this. I could split it apart like this. Would not be super safe, right? We don't want to go around generating chlorine gas. This is not something we would do in class. That would be dangerous, not good for you. But I could, in theory, make it happen. Now this next part is not technically in the class anymore. I am going to teach it. I am going to ask you to know how to do it. It's not hard. the reason I'm still including it is it's used everywhere. I find it pretty crazy that they say it's not included. I mean, you can't open a single textbook anywhere. You're not going to find very many practice problems out there that won't be using this notation. So in order to help you have access to as much practice as you can, I'm going to show you the little shorthand that gets used to describe a chemical cell. Because honestly, most people don't want to have to sit around drawing their little beakers all the time, do they? So they'll just kind of have a shorthand that would describe the parts of the cell without physically drawing them. We are going to see formulas listed, and they're going to be separated by vertical bars. Single bars, double bars. Electrodes go on the outside, and the solutions that are in the beakers go on the inside. We always list the oxidation first and the reduction next. The single line is what they call a phase barrier. So think about it. This is solid and this is a solution. Sometimes you may have more than one electrolyte. The reasons for that are a little above what we're doing, but you may see that. And if that's the case, they may list them in the same area, but they'll separate them with a comma. Sometimes we would use what's called an inert electrode. It's not going to be participating directly. They may add the concentrations. So you may see some other little things thrown in there, but it's not going to be overly complicated. It's going to follow this same pattern. The double line represents that thing we have to have included to make our cell work, which is that salt bridge. So let's look at an example. If we have this, here's my anode, anox, oxidation. I can see here I have zinc and sulfate ions. The solution was zinc sulfate. The zinc is the one that's really participating, right? This time I don't have a salt bridge, but I do have a porous partition. Over here, my copper sulfate is a source of my copper ions. And my solid copper electrode over here. So you can see people may just want to write this one line rather than draw this entire thing. So I know I've thrown a lot at you. This was not the shortest video ever made. There's a lot of little pieces to doing these cells, but the nice thing is once you kind of get your checklist figured out, once you kind of get the direction that things tend to go, they can be very repetitive, which is good. That's not a bad thing, right? It means we can get to the point where we're very fluent at doing it. So I actually took the time to try to type up an actual checklist, okay? Lots going on here, isn't there? You should have a little glue in for your notes that you can use as a reference to make sure you meet all these little requirements. Figure out what's being reduced and oxidized by looking at your chart, or do what they tell you, even if it's going opposite of what you'd expect. Draw your beaker. Make sure there's liquid in your beaker. Make sure your strips of metal for your anode and cathode are actually submerged in the liquid. Label what your solutions are. Put the ions that are there. Tell me what's anode and cathode. Tell me what metal your strips are. Put your pluses and minuses. Put your half reactions there, right? I'm telling you, it's very helpful. Make sure there's a wire connecting your strips. Draw an arrow and tell me where the electrons are going. Make sure you got a salt bridge. Make sure your salt bridge is actually sticking into the liquid. And then also don't forget to tell me which direction the ions are going. Right? You got to show me which way are the potassiums going, which way are the chlorides going. Okay. So these are the kinds of things, right? You got your electrodes, you got solutions, you got what type of salt bridge. Is it galvanic or electrolytic, right? All things that we want to make sure we include. So if I know this, for example, let's say we have zinc and copper, and I have these solutions, and I'm telling you I want a galvanic cell with this type of salt bridge, can you pause the video and can you actually draw that for me? So using those specifics in green, draw me what that cell would look like. Label everything you can. Pause it and actually give it a try. All right, let's see how you did. My first step is to figure out which thing will be oxidized and reduced. I'm going to go off of my reduction table, and since I was told it was galvanic, I'm going to pick the one that would prefer to be reduced and let it actually be reduced. So I have this, and I have this. I look at my chart, I get negative 0.76 and positive 0.34. This one is more positive, so that one will be reduced. And remember, red cat, reduced is cathode. That makes this one an-ox. Anode is oxidation. Leo, right, goes Gur. I have my cell. Look at all these things on here. Okay. I have a zinc electrode. It's going to be the anode. It's going to have a loss of electrons, so they're going to leave that anode. That makes this electron rich because they're leaving this area. They're going to come down here to this poor electron deficient side, the positive side. My red cat, that skinny little cat's going to start gaining electrons and gaining mass. I have a salt bridge in here. This time it was potassium chloride. I have some half reactions. I even have the line one down here, right? Only thing left, let's figure out what ions are floating around going which ways. So here zinc sulfate is soluble, copper sulfate is soluble. So those really should be broken apart. Here, if we're losing electrons, we're going to be forming more zinc ions, so I need some negative chlorides to come balance them out. Over here, we're going to be losing copper. It's going to get stuck on as neutral metal, so I need some positive chlorides being added. Sometimes they will give you a diagram that is so large with the salt bridge that you could even put the ions inside the salt bridge. You could write K plus inside here going down this way. Okay. Now, don't let this confuse you. This is a voltmeter that measures the current. That's not the same as an outside electrical source. That's not the same as hooking it up to a battery or something, okay? Don't let that bother you. That's just a way to measure how much is actually going through your wire. All right, you finally made it to the end. You're getting real close to the end of the year. There's a little bit more to learn. I think if you practice your cells, you can practice drawing them, you can scrounge up quite a few points, right? And they're adding more of those diagram type questions to the exam lately, aren't they? So I would expect to see something related to drawing a cell or labeling a cell. So it's really important you practice and get pretty good at it so you can scrounge up a few more points on that test, okay? All right, everybody, that is it. I hope that was helpful. Bye.